Hi, welcome to videos on RC circuit. So in this video we see the transient response of RC network. So let us consider a capacitor C, and it's connected to a resistor of value R through a switch S S1. Okay, let us assume that we have an initial voltage across the capacitor which is V naught being stored across the capacitor parallel plates. So this is the voltage that is stored when the switch is open. So we want to just analyze how does the capacitor voltage behave as the switch is closed. So we are trying to find out. So from t is equal to 0, so at this time t is equal to 0, we know that the capacitor voltage, so if I say this as Vc of t, when t is equal to 0, then Vc of 0 is equal to V naught, because when the switch is open the capacitor voltage is actually V naught. That's what we are assuming. So we want to see, as we close the switch at t is equal to 0, what is the behavior of the capacitor voltage, what is Vc of t as t is greater than 0. So because at t greater than 0 we are actually closing this switch S1. So to understand the working of this particular very simple circuit of a RC network with a capacitor with an initial voltage of V0, so let us write the equivalent circuit of this circuit when the switch is closed. When the switch is closed, this circuit will exactly look like this. This is R, this is C, and we know that this is having a voltage V0, and let us consider this as node A. So let me consider current IC, and there is a current IR. So writing KCL at node A will give me the current that is leaving node A is, one of the current is IC, the other current that is leaving is IR, and there are no currents entering the node. So that's why it is IC plus IR is equal to 0. If you consider actually what is IC, so it is C into dV by dt plus, okay, now the current that is flowing through the resistor is the voltage what we have across the capacitor divided by, so we have the resistance R equal to 0 now. So what I'll do now is, so you can just rewrite this as dV by dt is equal to minus of V by R. So let me slightly rearrange the equation. So let me write it as dV by dt is equal to minus of V by RC. Let us do the cross multiplication. So let me write it as dV by V is equal to minus dt by RC. Now since we want to know how does the value of the capacitor voltage varies as the time elapses, let us integrate this entire thing over a period. So let me just do this dV by V, so with an integration starting from V0 to V of t, and then let us do the integration of this from 0 to t, which is now minus dt by RC. So upon taking the integral, we'll end up with this as ln of v, so with the limits as v0 and vt, and this becomes minus of t by RC, applying the limit 0 to t. So then this reduces to ln of v of t minus ln of v naught is equal to minus of t by RC, which can be further written as ln of Vt by V naught is equal to minus t by RC. Now taking the exponential on either side, so the exponential of this happens to be Vt by V naught is equal to e power minus t by RC. So if you further rewrite this, so then this reduces to Vt is equal to, of course, this is now equal to V0 into e power minus t by RC. So if you can see, this is the expression for Vt which happens to be the voltage across the capacitor. So this Vt is nothing but voltage across the capacitor at a given time. At a given time is given by V0 multiplied by e power minus t by Rc. So this V0 is the capacitor voltage that is stored initially. So what we can do now is, if the capacitor initial voltage is V0, if you close the switch, with the capacitance value as C and the resistance value as R, we know that. So we are interested in trying to know what is V of t, which is the voltage across this capacitor as time elapses. If you can see here, V naught of t, if you substitute t is equal to 0, which corresponds to the point at which you are closing the switch. So if this is t, at t is equal to 0, if you substitute t is equal to 0 to this expression, then V of 0 becomes V naught, meaning the capacitor voltage at the time of instant of closing the switch is actually the initial voltage across the capacitor, which is V naught. Suppose as you increase the value of t greater than 0, so because of this term, this V naught, whatever the value of Vc of V of t you have, will be start reducing exponentially. You can see this is keep reducing exponentially. The rate at which it reduces purely depends on the value of R, C as well as the value of T, at what time you are seeing and what is the corresponding values of R and C. So usually this value of R and C, that is R into C, will be also known as time constant tau, so that we can write the expression for the capacitor voltage as V of t is equal to sorry, the initial voltage multiplied by e power minus t by tau, where tau is equal to R into C, which happens to be the time constant. So tau is now R into C, which is in seconds, and of course t is the time at which you are trying to find out the response of your capacitor voltage at a given time. Suppose if you consider T is equal to RC, with the value of R is equal to 1 kilo ohm and the value of C is equal to 1 microfarad, then tau happens to be 1 millisecond. Suppose if you try to find out and if you assume that the capacitor voltage, initial voltage is equal to 10 volt, so assume that if capacitor voltage is 10 volts, and if you want to see what is the V of t at t is equal to 1 millisecond, which happens to be 10 into e power minus 1 by 1. So then this will be exactly because this is 10 into 0.368, so this will be 3.68 volt, meaning at time is equal to 1 millisecond, with the value of R is equal to 1k and the value of C is equal to 1 microfarad, with the values of R and C, these values, and upon closing the switch after 1 millisecond, if the capacitor initial voltage is 10 volt, after 1 millisecond the voltage across the capacitor reduces to 3.68 volt, 68 volt. If you further allow it to discharge, then it is keep on discharging and it becomes 0 at t is equal to infinity. So likewise, at each and every point we can able to find out what is the value of the capacitor voltage at any given time. Assume that if you want to know what is the value at 10th millisecond, so what you can do is, it is V of 10 millisecond is equal to, it is 10 into e power minus 10 milli by 1 milli, so it will end up with this. So you have 10 into e power minus 10, so whatever the value that comes out, it is 10 into e power minus 10, so that will be the corresponding value. Suppose if you want to find it for some other time, just keep on substituting this with that time, so that this t will change, tau remains same, and it happens so let us try to understand the usage of this particular equation by taking few examples. Is equal to V naught into e power minus t by tau, where tau happens to be the time constant of the network, So after understanding this particular expression for the capacitor voltage whenever it is connected to a resistor of value R, so let us take up this example and try to apply those equations and try to understand it better. So in this example, let us take the first example. We are being given, so there's a 12 ohm resistor and there is a 6 ohm resistor, and then we have a 8 ohm resistor connected here and have a capacitor of value, okay, 1 by 3 farad, 1 by 3 farad. So what is asked here is, so Vc of 0 is given as 60 volt. We are asked to find out what is the voltage of capacitor with respect to time, that is Vc of t, and we are asked to find what is Vx of t, where Vx is the voltage across this 6 ohm resistor. This is Vx, and then we are also asked to find what is the value of I naught. What is the value of I naught of t? So the initial voltage across this capacitor is 60 volt. We are asked to find what is the VCT, that is voltage across the capacitor with respect to time, and what is the voltage across this 6 ohm resistor, and what is the current flowing through this 8 ohm resistor. So for this particular problem, so what we know is, we know this type of equivalent circuit. So we know what is this. So this is RC, and if I can able to bring the given circuit onto this form, then I can able to use the expression of Vc of t is equal to V naught e power minus t by RC. So first and foremost thing is that we have to bring this particular circuit into this form, and then we can able to find out the value of R value, and of course the C value is that is already given. So we have to find out actually what is the value of R. So in order to bring the given circuit into the standard circuit, so we may have to consider, you can see these two are coming in parallel. So we have to find out the equivalent resistance of this, and then that is coming in series with this. Suppose if you find out what is the now this you can reduce to a single resistor here, and then there is a 8 ohm resistor. This is actually, I think this comes out to be 12 into 6 by, so, and this becomes 18, and then we have this capacitor, okay, this is 1 by 3, so this is okay. Now you can see this happens to be, I think this is 4 ohm. So, and then we will end up with this, because now these two will come in series, we will end up with a capacitor of 1 by 3 farad, and we have a resistor of 4 plus 8, 12 ohm. So this is now exactly in line with the expected circuit. So we have a capacitor of 1 by 3 farad, there's a resistance of 12 ohm. Now I can find out what is the value of tau, which is nothing but RC, which is equal to 12 into 1 by 3, which is now 4. So this is now the value of tau is actually 4 seconds. Now let us try to get the expression for Vc of t, which is nothing but V naught. V naught is nothing but the initial voltage across the capacitor, which is now 60, and it is e power minus t by Rc. Rc is equal to actually 4. So this comes out to be 60 e power minus 0.25 t. So this is the expression for the capacitor voltage with respect to time. So it decays with this rate. It is e power minus 0.25 into t, because this 0.25 you are getting because this 0.25 is actually 1 over tau. 1 over tau. And then we are asked to find out what is Vx. Vx is nothing but the voltage that is there available across the resistor 6 ohm resistor out of the capacitor voltage here. Now I can just treat this as, you have a capacitor voltage which is of Vc of t, and I have a resistor of 8 ohm, and I have an equivalent resistor of I think it is 4 ohm. So whatever voltage that comes across 6 ohm, the same voltage will be there across 12 ohm also. So instead of writing Vx as this, I can write this also as Vx, this also as Vx of t. So from this expression, from this circuit diagram, I can write Vx of t as equal to Vc of t multiplied by 4 ohm divided by the overall resistance. This is like a potential divider. Overall resistance is 8 plus 4, which is 12. So now I know what is this is. This is actually 60 e power minus 0.25 t into 4 divided by 12. So this is now 3. Now this comes out to be, so now Vx of t is equal to 20 e power minus 0.25 t. This is the expression for the voltage across this resistor of 6 ohm at any point of time. So if you want to find what is the value of the voltage across this capacitor at 2 seconds, you simply substitute t is equal to 2. If you want to find it at 1 millisecond, substitute the value of t as 1 milli. So we can able to get the expression, or we can able to get the exact value of the voltage across the resistor. And then we are asked to find what is the value of I naught. What is the value of I naught? So I naught is nothing but because I naught is the current that is flowing through 8 ohm resistor. Since this 8 ohm resistor is actually in series with this entire resistor of course this way happens to be 4 ohm. So now this is what is I naught, and you can say this is I naught, this is I naught. So I can find out what is I naught of t. So from this circuit diagram, so whatever you have now is, so now this is 4 ohm and this is 8 ohm, and then you have a capacitor voltage which is with respect to time as Vc of t, and you're looking at current I of t or I naught of t. I can write I naught of t as equal to Vc of t divided by, that is voltage divided by the entire resistance. Resistance is actually 12 ohm, because because these two are in series, the resistance comes out to be 12. Then I can write it as it is 60 e power minus 0.25 t by 12, which happens to be now 5. So I naught of t is equal to 5 e power minus 0.25 t. So from this example, we can able to use the expression of V of t, that is voltage across capacitor t is given by V naught into e power minus t by RC. To find out the value of R, we actually found out the equivalent resistance, which was coming out to be 12 ohm, equivalent resistance of the entire network, which is the parallel combination of these 6 and 12 ohm resistor, that is 4 ohm, that is coming in series with this 8 ohm, which has become 12 ohm, and that 12 will be the value of R, and of course we have been given the value of C. So we end up with the expression for voltage across capacitor, voltage across this resistor 6 ohm resistor, and the current through this entire 8 ohm resistor, which happens to be the overall current in the circuit. Okay, let us also try to work out more problem where you have something like this type of circuit. So let me consider a voltage source which is now 24 volt is given, and I have a 6 ohm resistor, and I have a switch, and there is a capacitor of value 1/6 farad, and I have two resistors which are connected in parallel. One is 12 ohm, other is 4 ohm. So what is said now is this switch S is closed closed at t equal to 0. At t equal to 0, this switch S is closed. This switch S is closed at t is equal to 0. We have been asked to find out what is Vc of t, that is voltage across the capacitor, and what is the energy that is stored in this capacitor. So Vc of course 0. What is the energy that is stored in the capacitor? To know what is the Vc of t, so we know that because here also you can see, even though we have a source here, sorry, this is not, switch is not closed, it's actually opened. Switch is opened at t is equal to 0. So why it is opened is initially it is closed. So what will happen is at t is equal to 0 second, I just open it. So before I open, it is actually in closed mode. Whenever it is closed, out of 24 volts, some voltage will be get stored in this capacitor, and that will be your V naught of Vc of 0. Vc of 0 is nothing but the initial voltage of this capacitor when this switch is closed. So when this switch is closed, we know that the equivalent circuit looks like this. So I can rewrite the equivalent circuit at t less than 0, at t less than 0, because at t equal to 0 I'm just opening the switch. So at t less than 0, switch is closed. Switch is closed. When the switch is closed, this is how the circuit is looking like. So I have a capacitor, and I have, of course, I'll write the equivalent resistance. Now this will be 3 ohm, so it is 6 ohm. So I have a 24 volt, and there is a capacitance of 1 by 6 farad. Now what is VC0? VC0 is nothing but the voltage across the capacitor before I open the switch. When the switch is closed, now this is a circuit how it looks like. So you can see out of 24 volt, because since it's a DC voltage, this capacitor looks like an open circuit for this DC. If you want to know what is the voltage across this, okay, VC of 0, I have to actually find out of this 24 how much is being dropping here. So we can actually find out what is VC naught, that is voltage across the capacitor when this switch is closed. It's actually 24 volt multiplied by 3 ohm divided by the overall resistance, which is 9. So if you solve for this, so this happens to be 3 and this is 8 volt. So the capacitor will initially hold a charge corresponding to voltage 8 volts, and of course we have a capacitance of 1 over 6 farad. So now we could able to know what is the initial voltage across the capacitor, which is equal to now 6 volts. So once we know what is the initial voltage, so we can find out what is VT, that is voltage across the capacitor at any point of time when the switch is actually opened. When I open the switch, how does the circuit will look like? The circuit will look like this. So it is now 24. This is now just a minute. This is now equal to 6 ohm. Now the switch is open. This is now 1 over 6 with 8 volt across it, and then you have a resistor of equivalent 3 ohm. Now what is this VCT? VC of t is nothing but V naught e power minus t by RC. Now we know the value of R, we know the value of C. So what is the value of R? The value of R is equal to 3 ohm. The value of C is equal to 1 over 6. So tau is equal to RC is equal to now is actually half. So if you want to know what is VC of t, VC of t is nothing but 8 e power minus t by half. So now this value of VC, that is voltage across the capacitor at any point of time, is given by 8 e power minus 2t. So this is the expression for the capacitor voltage when the switch is open circuited. Because when the switch becomes open, so we will end up with there is a capacitor voltage, initial voltage of 6 volt will be start dissipating across resistor with this expression. Of course we can find the value of energy, that is charge that is stored in this capacitor, which is now given by VC of 0 is given by the expression. Let me just write it. So I have a equivalence. VC of 0 is nothing but half CV square. I know the value of C as 1 over 6 farad. I know the value of V, which is equal to 8 volt. So naturally, because we are looking at T is equal to of course just before the opening of this switch, okay, what is the charge that is stored in this capacitor, that is energy stored in this capacitor? It is now half into 1 over 6 multiplied by, so it is now 64. You end up with, so this is now 2, so now you end up with 32. It is 32 by 6, happens to be 5.33 joules of energy stored. So This is the value of the energy that is stored in the capacitor before I open the switch. Okay, once I open the switch, it will start dissipating. Across. Okay, because of this, resistor is coming in parallel with this. So this way we can able to use the expression that we derived in this particular video, which is a capacitor will certainly discharge. The capacitor will certainly discharge. Suppose if this is R, if this is the value of C, and this is V0 is the voltage across the capacitor initial charge, and if you want to know what is the capacitor voltage at any point of time, we know that if this is V0, depending on the time constant, because V of t is given by V0 e power minus t by RC. Of course, this can also be written as V0 e power minus t by tau. If tau is too large, it decays slowly. If tau is slightly larger, of course it decays a bit fast. If tau is very small, then it decays quickly. You can see it decays very quickly. So this is how, of course, this discharge of this capacitor voltage purely depends on the value of tau. It is actually inversely proportional. If the value of tau is less, it discharges quickly. So when the value of tau will be less, if the value of RC time constant is less, then it discharges very quickly. Okay, this way we can able to understand the working of this RC network in the absence of a source. So there is no source existing, but still we are assuming there is a voltage of V0 being stored across the capacitor before I connect a resistor to the capacitor so that it starts discharging.